I want to take a quick look at how Forth Haiku compiles and optimizes a simple expression. Here's the expression we're interested in. It's going to add x and y. So it pushes x, pushes y, and then calls plus. That's standard Forth practice. So if we look at this expression and we look at the code in Forth Compiler.js, we see the x gets pushed, so it's this first thing here. Then y gets pushed. And then we scroll down and find plus down here. Those are the cause of these three instructions. So there's push of x, the push of y, and then the push of the plus of x was pushed first, that thing, and then y here, and then we plus them together, and then we push the result. So we've popped these two off, and we do a push. So there's one thing left after this. X pause and Y pause get passed into this function as parameters. They're basically meant to be constant shader parameters that come in and affect every pixel on the screen. The part that we're interested in today is how all that gets compiled down to this kind of JSON. First, we do the compilation to the simple stuff, and then we run a second pass that reduces the generated code to that. Let's look at how that works. We look at StackOptimizer.js, and we notice that it keeps several global variables. We're not going to worry about the return stack or the call stack. So we are interested in dstack and temp index, and then there's one more thing called code, which is just an array of the code that gets generated. On this side, there's also this thing called bogus. When there's some kind of error, stack underflow or something, then it just fires out a stock set of answers. It should be 4 items. So the top 4 items, 0, 1.0.7, and 0, and then a 1. I think that gets ignored. And I'm just going to ignore this whole case for right now. So what happens? So we walk through this code in sequence, and we look at it line by line. So we start with that line, and we go down to here, that line, and it says step 1. There are no pop calls here. There's no pop in here. And we do see a dstack.push, which will fire up code here. It matches. So it basically does a match on the string. And if it sees a dstack.push of anything, it executes some code. And what's that code? It creates a new temp, bumps the index for the next temp. In the new code, the regenerated code, it pushes temp1 gets xpos, and then it pushes temp1 onto the simulated stack. The second statement is almost the same. So then we end up with code that says temp1 and temp2. Simulated stack contains the name of the variable temp1 and the name of the variable temp2, and the next temp that will be generated is 3. Then we get to the third statement. So we grab that whole line, stuff it into S, and then we find that there's a match against pop. Where is it? It's here. Dstack pop. It changes the stack to be temp2 plus another pop. So then it continues on, it finds the other pop, and then it replaces this part with temp1, and then pushes the result on the stack. It's popped everything off of the simulated stack, so it's now empty. It was working on the value part, and it replaced the value part with that. And now it's going to create a new temp, and then going to create temp to be this, which ends up here, emits that piece of code, and then pushes temp3 onto the simulated stack. So now the simulated stack has temp3, and the optimized code contains 3 lines, temp1, temp2, temp3, and the next temp will be 4, which in this case we won't reach. And then at the very end, it just pads to make sure there's 4 values on the stack. There's only 1 value on the stack at the moment, so it pads it out, and we get this. And then it dumps out the code that was generated. It dumps out the padding. That's the end.